In this section, we will discuss the other important subatomic particles besides electrons and how these subatomic particles come together to form atoms. Ernest Rutherford was instrumental in helping develop the so-called nuclear model of the atom, and we will discuss one of his very famous experiments in detail. Rutherford performed an experiment that helped us understand the so-called nuclear model of the atom, which is a model that places most of the mass in the center of the atom. And so this was done by taking advantage of radioactive particles that were produced by radium, which was discovered by Marie Curie. These alpha particles were focused on very thin sheets of gold, known as gold foil, and the interaction of the alpha particles with the foil provided quite a lot of information about the structure of the atom. It turns out that these alpha particles are essentially helium atoms that have had the electrons removed from it, and so in essence alpha particles are the nuclei of helium atoms. We know that these alpha particles have a 2+ charge, and that these alpha particles had mass which was considerably less than most of the elements. And we also know that alpha particles are not particularly good at penetrating through anything that has a significant amount of mass. So it was a bit of a challenge to actually get these alpha particles to go through the gold foil and be able to observe them. This represents a schematic diagram of Rutherford's gold foil experiment. On the left here you see a source of alpha particles. This might be radium or some other radioactive material. It's placed inside a lead box, typically for shielding purposes. The box would have an opening that allows some of the alpha particles to escape, forming a beam of alpha particles, which are then focused onto the surface of the gold foil. The majority of the alpha particles pass straight on through, with a small number of them being deflected at small angles, and also a very small number of them being deflected backwards at very high angles. The alpha particles are detected using a photographic plate, and the plate is then developed to see the positions of where the spots are located. Rutherford had to come up with some sort of explanation for these observations, and so he speculated that the gold foil involved gold atoms that were touching one another, and that the gold foil comprised of layers of gold atoms that were perhaps as thin as 2 layers. And the atoms were comprised of a spherical object where the nucleus, the center of the atom, contained the majority of the mass of the atom, and then surrounding this were the electrons, and they were very, very small particles. And but they defined the majority of the volume of the atom. So in this particular diagram, we have the alpha particles, which are comprised of 2 protons and 2 neutrons, and then the gold atoms, which have protons and neutrons right in the middle. These are the colorless and blue balls. And then the red little dots surrounding the nucleus in each of the gold atoms represents the electrons. Most of the alpha particles pass through the empty space, colliding with nothing, neither the nucleus nor the electrons. However, occasionally the alpha particles would come close to the nucleus, which was positively charged. Since the alpha particles themselves were also positively charged, objects that have the same charge tend to repel one another. If it was not a direct hit of the alpha particle with the nucleus, then the alpha particle would be deflected at a small angle. However, if the alpha particle had a direct hit or a nearly direct hit, then the alpha particle would be deflected at a very high angle. The conclusions that could be made from the gold foil experiment is, number one, that the majority of the mass of the atom is located in the nucleus, and the nucleus must be positively charged. Since we knew that both protons and neutrons are comprising the majority of the mass of the atom, it was concluded that these 2 particles were in the nucleus. We also knew that the protons were positively charged, so that was consistent with the nuclear charge. And surrounding the nucleus were very, very tiny negatively charged particles, the electrons. And the electrons essentially were so small that they didn't interact effectively with the alpha particles. The electrons were the thing that defined the overall volume of the atom, however. And so from this we could get an estimate of the relative size of the nucleus in comparison to the size of the atom, and it was estimated from the gold foil experiment that the nucleus is approximately 15 orders of magnitude smaller than the size of an atom, which is about an angstrom or slightly larger. Our modern view of the atom is very much based upon Rutherford's experiments. We now know that the nucleus of an atom is comprised of 2 subatomic particles, the protons and the neutrons, which roughly have the same mass. They are considerably bigger than the electrons, and they are located as a group in the center of the atom. The electrons, which are much, much smaller, are surrounding the nucleus, and they are the ones that define the volume of the atom. We know that the proton is positively charged while the neutron does not have a charge, and we also know that the proton and neutron are roughly the same mass. In this particular table, we show the mass in terms of the atomic mass unit, which is equivalent to 1.66 times 10 to the negative 27th kilograms. An obviously not very convenient number to work with in terms of kilograms, hence we say that this is equivalent to 1 AMU. In the diagram that is shown here, we have an atom with 11 protons. This would be the number of protons in a sodium atom. The number of protons always defines the element that you are dealing with. And the total mass of this particular atom is roughly defined by the number of protons and neutrons together. So this atom would have a mass of approximately 23 AMUs. surrounding that nucleus must be the same number of negatively charged particles as there are positively charged particles in the nucleus, so hence there must also be 11 electrons to give a net neutral charge. So we know that the electron is the negatively charged particle, yet its mass is extremely small, essentially non-existent in comparison to the protons and the neutrons. To define the element that we are dealing with, we define what is called the atomic number. The atomic number of an element is essentially the number of protons. And this is, of course, the number of positive charges in the nucleus. It turns out then that on the periodic table, we represent all the different elements with an atomic symbol. This is typically a 1 or 2 letter symbol. The first letter is always capitalized. If there are 2 letters, the second letter is always lowercase. And so in this particular case, the atomic symbol for sodium is Na, coming from the Latin name natrium. We place this symbol inside of a box and then provide some additional information. In this case, above the atomic symbol in the box is the atomic number, which is 11, which then tells me there are 11 protons for sodium. Below the sodium is the atomic mass. And so in this particular case, since there are 11 protons and 12 neutrons, the atomic mass is essentially 23. So, in addition to the information inside the box on the periodic table, we also have a way of representing a particular atom of sodium by writing the symbol. Superscripted to the left of the symbol is the mass number, in this case 23, and subscripted to the left is the atomic number, the number of protons. So, anytime you want to know how many neutrons there are for a particular atom, all you have to do is take the mass number and subtract the atomic number, and that would give you the number of neutrons. So 23 minus 11, of course, is 12.